Okay, let's reconvene. So I think a couple more parts and we should be done. Chapter 29. So let's take a look at the following problem. Let's imagine we have two wires. One wire there. Another wire here, and these wires extend pretty far in both directions. And, we're going to say that each of these wires has a current going through it. So we're going to call this I1, and we're going to call this one I2. Okay. And you know what? I'll use lowercase. I'll use lowercase. Been staying with lowercase so far. So I1, I2. And we're going to be saying that those currents are in the same direction. Okay. So the other problem would be to have two wires where the currents are actually going in opposite directions, but remaining parallel to each other, or in that case, anti-parallel. So we're going to assume that that there's a distance between these wires R, and that there's a length here, a relevant length that we'll talk about, and you'll see why that comes into play. But typically at the end of the day, one will talk about a force per unit length, which is what we're after. So the problem is the problem at hand is what's going to be the interaction between these two wires. Now this problem is complicated because we have both magnetic phenomena going on here, right? So each of these wires is going to generate a magnetic field, and then each of these wires is going to react to that magnetic field and have a force exerted on it. So let's then redraw this. So here's wire 1. Okay, so here's wire 1. Current going through it, I1, and obviously these wires are going to have to be connected to a source of EMF in order to have that current established, but that's outside this picture, okay? And so we can ask ourselves, right? So what is going to be the magnetic field? What is going to be the magnetic field at a distance r? At a distance r from that wire. And so we could figure that out in magnitude. In magnitude, that's going to be equal to mu naught times I, in this case I1, over 2 pi r, where r is the distance in question. That's in magnitude. If we use the right-hand rule, place our thumb along the direction of the current, our fingers are going to curl into the direction of the magnetic field, and so at this point, the magnetic field is going to be into the plane of the board. So this is going to be into. Okay? And no matter where we are, right? Again, this remember this wire is very, very long. Right? It's a very, very long wire. And so no matter where we are at this distance r away, right? So if we're distance r away here or distance r away here, then the magnetic field is going to be the same at all points r away. So magnetic field's going to be into the plane of the board here, or paper rather, into the plane of the paper here, into the plane of the paper here, into the plane of the paper here, and it's going to be of magnitude mu naught I1 over 2 pi r. So that's the magnetic field. As a matter of fact, let's call this the magnetic field generated by wire 1. Call it B1. Okay? So what we're going to do now is we're going to take wire 2 and put it into that magnetic field. There it is. We're going to take wire 2 and we're going to place it right at that distance r away where that magnetic field is. And again, we have a current going through this wire, I2. And so now what happens is wire 2 is going to experience a force due to the magnetic field generated by wire 1. As a matter of fact, we know what that is. So the magnetic force on wire 2 is going to be equal to I L B sine of theta. But we got to be really careful here now. So now what I is this? This is the current through wire 2, so that's I2. L is going to be the length that we talked about earlier. It'll be the relevant length, so this will be some length that we're talking about. And so what's B? Well, B is going to be the magnetic field which is generated by wire 1, so we'll call that B1. And then the angle theta is 90 degrees, right? So this is the angle between the current direction and the magnetic field direction. Okay, so that's going to be 90 degrees. So this then becomes the force on wire 2 is going to be equal to I2 L times B1, but B1 is mu 0 I1 over 2 pi r, and this is in magnitude. Okay, so let's clean that up. So this is the magnetic force on wire 2 is going to be mu 0 over 2 pi r. It's going to be I1 times I2 times L. Okay? Now that's all well and good for the magnitude, but what about the direction? Okay, so there we need the first right-hand rule that we talked about. So we would place our fingertips along the direction of I2, curl them into the direction of the magnetic field, which is into the plane of the paper, and our thumb would point upward, which then is going to be the direction of the magnetic force. So then on this wire, right, there's going to be a force, right? This would be FB on wire 2, FB on wire 2, FB on wire 2, FB on wire 2. So that bottom wire now, right, where I2 is running through it, is going to feel a force in the upward direction. Let's look at it now from the perspective of wire 1. Okay, so this time what we're going to do is we're going to look at wire 2. I'm going to look at wire 2. Again, wire 2 has a current going through it, I2. And again, this wire is very, very long. It's going to extend very, very long in both directions. And what we're going to ask ourselves now, what is the magnetic field generated at some distance r away? And again, we can answer that question, right? I'm going to roll this up ever so slightly. Okay, and so we can ask ourselves, what's the magnetic field? The magnetic field is going to be equal to mu naught over 2 pi r times I. In this case, it's going to be I2, and so we'll call that the magnetic field B2. And using the right-hand rule, this is going to be out of the plane of the paper. And so then it doesn't really matter what distance we are away as long as we maintain it it doesn't matter where we are along the wire as long as we stay a distance r away. The magnetic field is going to be out of the plane of the paper. Okay? So now what do you think we're going to do, right? We're going to put wire 1 back in. I'm going to put wire 1 back in. There it is. There's wire 1. Remember that wire 1 has a current going through it in this direction. That would be I1. And so now wire 1 is going to feel a magnetic force from the magnetic field generated by wire 2. And so the magnetic force on wire 1 is going to be then I L B sine of theta. What I is it? It's the I that is going through wire 1. Remember that L is the relevant length, some length L that we're talking about here. B now is going to be the magnetic field that was generated by wire 2, so that's B2. And so we now have FB is going to be I1 times L times B2, which is mu 0 I2 over 2 pi r. Sine of theta is equal to 1 for reasons that we discussed above. That is that theta is equal to 90 degrees. The direction of the current is perpendicular to the direction of the magnetic field. And so we can clean this up. Remember, this is just in magnitude. All right, so we can clean that up. The magnetic force on wire 1 then is going to be mu 0 over 2 pi r. So it's going to be I1 times I2 times L. And you'll notice that it is identical in magnitude to the force on wire 2. Okay? So the force now is identical in magnitude to the force on wire 2. Its direction, though, let's look at its direction. So its direction is going to be, if we place our fingers along the direction of the current, curl our fingers into the magnetic field, which is coming out of the plane of the paper, then this wire is going to feel a force, a magnetic force in the downward direction. So this is the magnetic force on wire 1, magnetic force on wire 1, magnetic force on wire 1, magnetic force on wire 1. So you'll notice in looking at these two pictures, right, that these two wires are going to feel a mutual force of attraction. Wire 1 is going to attract wire 2, and wire 2 is going to attract wire 1. So when when the currents are in the same direction, the wires will experience a mutual force of attraction. So now, if the currents are in opposite directions, then the wires will experience a mutual force of repulsion. And I want you to show that. All right, I want you to go through the same logical and mathematical arguments that I used above to show that for currents in opposite directions, one will have a mutual force of repulsion. Okay, I'm going to end this part here, and then we'll have one more part to just clean up some loose ends and show you just one more current distribution, and we'll talk about that a little bit. Okay, signing off. Stay tuned.